I'll try to answer the two questions. First, the significance and interpretation of Sommerfeld number, which is given as R by C whole square mu n by P. The usual meanings are R is radius of the journal, C is the bearing clearance, mu, that is the lubricant viscosity, N is the shaft speed, and P is the projected load. And the second part, what are the permissible limits of Sommerfeld number for bearing operation? The answer will come first in terms of the physical interpretation. You can have a look at the whole expression in one go. If R increases, that is, if you consider a larger size bearing, if it is working with a lubricant which is very viscous, say a thick liquid, if it is running at a very high speed and load is low, projected load is low, in that particular case it will register a bigger Sommerfeld number. Whatever phenomenon that comes into existence due to this type of relationship, it will remain exactly the same in case you try to lower down the clearance. That means if you work with a very tight fitted bearing. Also, in case you progressively go on decreasing the pressure, projected load, obviously in that particular case also this will register a bigger Sommerfeld number. So basically, none of the parameters alone decide what will be the value of the Sommerfeld number, but this dimensionless cluster, there are two clusters, one is R by C whole square and second is mu n by P. This comes into existence by virtue of the lubricating oil, speed and the projected load. So this part, this is associated with the bearing and this is associated with the journal. In place of R by C whole square, we could have used R by C only. In place of mu n by P, we could have used, say in place of P, projected load, we could have used the total load also. But the most significant parameters are the projected load, mu n, and not R by C, but R by C whole square. This particular relation, why it has been written like this? The foremost reason is this dimensionless cluster, which has been named as the Sommerfeld number, this has been utilized by the pioneer researchers of Westinghouse Research Lab, Raimondi and Boyd, to solve the classical Reynolds equation, which has been published way back in 1958. And there are 3 papers. I have mentioned those 3 papers in my notes, which was uploaded. If you feel like, you can manage a copy of that and read it. And you'll see that whatever is available in my notes or in the book of Shigley, the 3 papers, they exactly have the same information. In fact, the book of Shigley, my notes, both of them, they have been derived from the published work of Raimondi and Boyd only. Now because all bearing design, they are based on the research work of Raimondi and Boyd only, and since Raimondi and Boyd, they have tried to derive all the relations in respect to the Sommerfeld number. That is the basic reason why we are compelled to use Sommerfeld number for our analysis. And for the purpose of interpretation, if you are working with a lightly loaded bearing, you are working with a high Sommerfeld number. If you are working with a very high loaded bearing, you are working with low Sommerfeld number. That means when you look at a scale which has the Sommerfeld number taken the 10th log of it, then a high load situation that indicates positions close to this, and a very low load situation that indicates a position close to this. The limits of Sommerfeld number for the purpose of analysis, that has been fixed from 0 to 10. Fundamental reason why it is so is, in the paper of Raimondi and Boyd, all tables, they have been reported only up from 0 to 10. This essentially means all the field of information that we have about behavior of bearings for particular Sommerfeld numbers, that range of 0 to 10 is the only range of knowledge which is available to us. So for all theoretical work, we'll consider only the range of 0 to 10. Now, the first part of physical interpretation that is taken here. Now, the second part of the question was, what are the plausible ranges? What minimum value and what maximum value of Sommerfeld number should be chosen when we design the bearing? For this, please look at this figure with due concentration. The x-axis, that shows the Sommerfeld number on a logarithmic scale. Fundamental reason why it has been taken on logarithmic scale is there is a great variation in behavior of the bearing in between Sommerfeld number of 0 to 1. Behavior of the bearing in the Sommerfeld number zone from 1 to 10, the difference is marginal. But if we draw a linear scale, obviously the majority of the plot, it will be occupied by 1 to 10, that is 90% of it, whereas the greater importance that lies in this 1%. That's why it has been logarithmically contracted. So from 0 to 1 and the remaining 90%, 1 to 10, is on this side. If you are not very clear about the logarithmic scale, you can revise your earlier studies. Here, 4 L by D ratios they have been considered. First is L by D ratio of infinity, that is an infinite bearing. L by D ratio of 1, that is a square bearing. L by D ratio of half and L by D ratio of 1/4. You'll see there are 2 lines running here which are printed in brick color. This sets the limit for maximum W, that is the maximum load to be carried. And the second line that indicates the minimum F. F, this stands for the coefficient of friction. W, this stands for the load to be supported on the bearing. This W is nothing but an indicator of the projected load. W divided by the projected area, that gives you P. Now, there are 2 applications. There are 2 purposes for which journal bearings are used. First, we want to minimize the parasitic torque as much as possible. For this, the fundamental requirement is we are targeting the minimum possible friction. And second, we want to bear as much load as possible on the shaft. So, if the purpose is to have the maximum load to be carried on the bearing, this particular curve that decides the limit. And for minimum coefficient of friction, that means the minimum parasitic torque or the minimum energy loss due to the bearing, this sets the limit. So this particular region essentially sets the limit in which the Sommerfeld number should be selected. So you can see here it is 0.4, and depending on what L by D ratio it works with, say for the ratio half or for a square bearing. For a square bearing it may be 0.002. For L by D 1/4 it may be fairly close to 0, and for an infinite bearing it may be greater, it may be say 0.0019. So this is the permissible limit of Sommerfeld number. Roughly you can take it as 0.002 to 0.4. Practically the effect of these two, it is self-correcting. It is for the fact, if you look at the y-axis, on the right hand side I have indicated HO by C, that is the ratio of minimum film thickness to the clearance. Minimum film thickness upon clearance, this ratio of 1, this indicates 100% concentric bearing, which is practically an impossible proposition. This never happens, as I explained earlier. And the reciprocal of HO by C, that is C by HO, that is termed as eccentricity, epsilon. This has been plotted on the right hand side. Here you can see Say you decided on working with a very low Sommerfeld number. Very low Sommerfeld number, it will arise when the projected load is very high, or the spin speed is low, or the lubricant is too thin, or the ratio R by C is quite small. Whatever be the combination, say you work with a very small Sommerfeld number. So as you work with a very small Sommerfeld number, obviously you are bound to obtain dimensionless minimum film thickness variable close to 0.1. That means only 10% of value of the clearance that will be available as the minimum film thickness. So only a small amount of lubricant will pass through the section of minimum film thickness, and obviously this will give rise to temperature inside the bearing. As the temperature rises, mu falls. As mu falls, very obviously you see that the Sommerfeld number has a tendency of falling further, because any drop in mu, it will lead to drop of S. So you find that the tendency of Sommerfeld number is to shift to the left. This is not a good proposition. But on the contrary, if you are setting the initial variable here, say Sommerfeld number of 0.4, at Sommerfeld number of 0.4, and say if you're working with a square bearing, you get minimum film thickness as good as 0.7. That means 70% of the clearance, that much of minimum film thickness is available to you. Obviously, in this particular case, you are bound to obtain a greater coefficient of friction. Since the coefficient of friction is high in that particular case, so obviously it will again try to heat up the lubricant. As the lubricant gets heated up, mu falls, and it will lead to a fall in the Sommerfeld number. So it will move to the left. This movement to the left, it is self-correcting in nature. As it moves to left, again the phenomenon, it will be such that there will be a fall in the projected load, there will be a rise of, there will be a fall in minimum film thickness, which will progressively change the behavior such that again it hovers to the right. So if you start your design from left, that is from a very small Sommerfeld number, this may not be a very good proposition. This may not be self-correcting. But on the contrary, if you start with a Sommerfeld number which is indicated by maximum W, so the highest possible one, that is 0.4. Here, with passage of time, this will have a self-correcting nature. So, in the nutshell, you always can take the range of acceptable or permissible Sommerfeld numbers to be from 0.002 to 0.4.